So this first lecture is going to focus on an introduction to electrical and computer engineering. Now why? Because circuit analysis, which is the topic that these lectures focus on, circuit analysis is a fundamental skill, a fundamental topic within most electrical and computer engineering educations. Now, one thing I should say here is that at several points I'm probably going to revert to saying electrical engineering as opposed to electrical and computer engineering. That's merely just a shortcut. I'm really referring to both the entire time. You'll see here that I've also included some supplemental YouTube resources. These are from other creators, not myself, that are related to what we're talking about here. So jumping right in, electrical engineering is the study, design, and application of devices and systems that employ electromagnetism, as well as electricity and electronics to solve problems, because that's what engineering is really all about, solving problems. For the next couple minutes, we're going to talk about some of the subfields that are included within, typically, within electrical and computer engineering. So let's jump right in. We have power and energy. Now this is first for me. This is actually the topic that I studied when I was in graduate school. So power and energy deals with generation, transmission, and distribution of power, electric power. Relevant components include transformers, electric generators, and electric motors. You can see here I've included some sample pictures. This is a picture of a gentleman placing the windings onto some sort of synchronous machine. Over here we have some wind turbines and some solar cells, and obviously those are two really important technologies for renewable energy. Another area is telecommunications. So telecommunications focuses on the transmission of information as electrical signals over channels such as coaxial cable, fiber optics, or wireless transmission paths. Often information must be encoded in a carrier signal via amplitude or frequency modulation. Many of you may not be familiar with those terms, but are very familiar with AM and FM radio, and that's actually where those names come from. AM being amplitude modulation and FM being frequency modulation. Engineers that work in telecommunications will design the antennae, transceivers, as well as amplifiers, linearizers, etc. All the components that make telecommunications possible. How do we transmit a signal, a relatively clean signal on one end, and receive that relatively clean and accurate signal on the other end a mere fraction of a second later? And so here you can see I've included some pictures relevant to telecommunications. Here you have a picture of a radio tower with some what looks like cell phone antennas on it. I actually did my internship when I was in college at Singular Wireless, which is no longer a company. It's part of AT&T now, but and as part of that internship I actually went on top of some buildings and worked with some of those antennae. Here we have what looks like some sort of a radio astronomy telescope, and then here we have some satellites, which I don't think I really need to tell any of you how important that is to global communication as a relay for wireless signals. The next area is signal processing. So signal processing deals with the analysis and manipulation of signals. This includes all kinds of processes that you're probably very familiar with: amplification, filtering, removing noise, compression, making file sizes smaller, encryption, making those signals less vulnerable to any sort of external manipulation, as well as error detection and correction, right? Anytime we send these high bitrate digital signals along some sort of transmission channel, it's inevitable that we will be losing bits here and there. And so error detection and correction is essential to maintaining a clear signal. Another area is controls. Controls focuses on the modeling of complex dynamical systems and the design of controllers to affect a desired behavior. So controls is, as the name suggests, about controlling something and making it do what we want to do. One prime example would be the self-driving car. It's a very complex control problem, one that requires all kinds of different sensors, acquiring image data, radar data, LiDAR data, all kinds of environmental information, supplying that to a computer that is required to do real-time calculations, essentially real-time calculations, and generate actuation signals for a whole bunch of different subsystems: accelerator, braking, steering. So engineers generally use closed-loop feedback systems, which, like I said before, monitor system behavior and make adjustments as needed. Now, one really interesting area that I would classify as sort of within controls, although I understand why many would disagree, is robotics. And I have students often that come to me and talk about their desire to go into robotics and whether it's prudent to choose electrical or mechanical engineering. So I always tell them you can't go wrong. They're both great majors. Both electrical and mechanical engineers, as well as other types of engineers, will work in robotics. Mechanical engineers design the frame, joints, all the physical aspects of a robot, and often ensure that they do not malfunction under stress. Very practical and important work. Electrical engineers often develop the higher level image processing, sensing, or artificial intelligence algorithms that allow them to use that frame in an effective manner. And this would include, stabilization if you're talking about something like walking on two legs. So control plays a really important role in robotics for both electrical and mechanical engineers. And we live in a world where the jobs of these engineers, respective engineers, overlap more than ever. So you have tons of mechanical engineers that are working in the same or working on the same advanced control problems as electrical engineers. Excuse me, at several points I'm going to say electrical engineer as opposed to electrical and computer. So please just go ahead and fill in the blanks. If you hear me say electrical, I'm really talking about both. Now the next area is electronics and microelectronics. So they deal with the design, implementation, and testing of electronic circuits. For example, let's say an engineer that works predominantly in signal processing. They've developed a specialized noise cancellation method for some sort of audio signal, okay? But they need to rely still on a colleague with electronics expertise, although nowadays it would probably be software. But let's go ahead and say that we need to use electronics for some sort of cost or speed reason. Okay, so this engineer relies on a colleague with electronics expertise to translate that method into hardware optimally. So the electronic engineer is often taking either processes, algorithms, objectives from other areas and implementing them as an electronic circuit. Almost all modern electronics are implemented, at least eventually, as a microfabricated or integrated circuit. And this should really come to no surprise to many of you, right? We're all, even over the past 5-10 years, have witnessed the drastic miniaturization of electronics, with one of the culminations probably being something like the Apple Watch, where we have an incredibly powerful computer that fits on a wrist. Another area that I consider closely related to electrical and computer engineering is biomedical. Now, if for many schools, or at many schools, this is a separate major, but I will discuss it briefly as sort of an area very closely related to electrical. So I consider it to be so closely related because biomedical applications rely on a lot of the same topics we talked about before. A lot of image processing, especially for things like cancer detection, wireless sensing, for different types of, obviously for sensing of human biometrics, and artificial intelligence, which also plays a huge role in sort of automated detection of disease. Some programs like ours, so I teach at the College of New Jersey, offer biomedical engineering majors for students with greater interest in biology and somewhat less interest in the fundamental engineering theory. So again, another really great major. Personally, I think that as an electrical or a computer engineering, you can still do a lot of really great work in the biomedical field. And then lastly is computer engineering. So historically, computer engineering was a subfield of electrical and then kind of evolved into its own monster. So let's talk briefly about what the difference between electrical and computer engineering is. So a computer engineer focuses on the design, implementation, and testing of computer architecture, systems, and hardware. So to take it even one level higher than that, I would say computer engineers are really more tasked with digital hardware specifically and software and the interaction between those two, whereas electrical engineers are a little bit more broad. You generally, if you're interested, let's say, in wireless communications or power and energy, those very clearly lie in the field of electrical engineering. And let's say you're interested in very large-scale integrated circuit design, I would say that really clearly lies in the field of computer engineering. But, you know, there are tons of topics related to embedded systems, sensing. I mean, I could give examples all day long that really blend or let's say muddle the line between electrical and computer engineering. I don't know if I said this already, but I actually did my undergraduate degree in computer engineering with a specialization in operating systems, and then moved on to do my doctorate in electrical engineering with a specialization in power systems. So computer engineers often also design the core software. So this could be the operating system, something as simple as a Python script, or if we're talking about an embedded system, some sort of microcontroller code required by that hardware. So a lot of hardware and software. Computer engineers are expected to have significant knowledge of digital hardware design, VLSI, very large-scale integration, artificial intelligence, and software development. They represent what I would consider to be the nexus of electrical systems and software. In short, electrical and computer engineering concepts and practitioners are, I feel pretty confident in saying, essential to the design of any modern technology. From computers to robots to smart bridges to biomedical technologies, think of any modern technology, and I challenge you to think of one that does not employ some sort of electronic or computer-based component. So electrical and computer engineering is a field that, in my mind, essentially guarantees a future-proof career in that field and multiple related fields, working with many engineers from other disciplines. So I think if you're a young person today and you're looking to choose a career and you have interest in electrical and computer engineering, it's a great choice. And so I think that the importance of EC only becomes more certain as predominantly mechanical systems, one example being the internal combustion engine, shift to more electric-based implementations, with the primary example being the electric vehicle or the EV. So now let's shift gears a little bit and talk about common electrical components. So the only reason why I do this up front is because in later lectures, when we talk about some of these, I don't want there to be a question mark in your head, right? I want you to have some basic understanding of what these are. It's going to start off really basic, so if it seems a little bit too much, I apologize, but I am trying to reach the broadest audience here. Okay, so common electrical components. First one is wires. I think most of you know what a wire is. It's a flexible strip of highly conductive metal, generally copper, used to short two physically separated points together such that the voltage potential at those points is the same. So we should be familiar with the term short, right? Short circuit. Essentially, when we short two points together, we're making them electrically the same, such that their voltage potential is the same. A conductor is a term we use for anything that freely conducts electricity. One example being copper, a wire. Now, very few things are perfect conductors, and so there is still going to be some resistance along any copper wire. On the other end, we have an insulator. So an insulator is something that does the opposite, blocking almost all current flow. Now, in reality, these are just two shades of the same color, right? Almost anything is somewhat conductive and somewhat insulating. The difference being that things that are highly conductive, like copper, we call a conductor, and things that are highly insulative, like, for example, wood, we would call an insulator or rubber. A switch is a component that opens or closes to break or complete a circuit. So over here we have a picture of an open switch, which then creates what I would call, or what we would call, an open circuit. So in this loop right here, no current will flow because there is no closed path. However, if we take that same switch and close it, we end up with a complete loop within which current will flow. The next component I want to talk about briefly is a resistor. A resistor, as the name suggests, resists the flow of current. We generally use them in electric circuit design to dictate the relative flows of currents and in turn control the behavior of a larger circuit. Now, one important equation we see right here is Ohm's law, essentially V equals IR, or you can see the form I've written here, I equals V over R. These are some examples of what common commercially available low wattage resistors will look like, and the bands on them, although I'm not going to specifically go into it, tell us what the resistance and the tolerance of the resistance value is. You can look online, there's tons of websites that actually will automatically decode those colors for you. So a resistor, in essence, as dictated by Ohm's law, allows us to manipulate the relationship between voltage and current. An operational amplifier, and you should be familiar with the term amplifier, allows us to increase the amplitude of a voltage signal by up to 100,000 times. Now this number, it depends on exactly what type of hardware we're working with, but let's say within some reasonable range. An op-amp, which is the common term for them, can be used to amplify transducer measurements coming in from sensors to increase signal-to-noise ratio and facilitate their display and digital storage. So let's say you have some sort of sensing device, you place it on the human skin, and it detects a heartbeat. If you were to take the output of that sensor and connect it directly to an oscilloscope, generally you're going to see a very weak signal, almost negligible when compared to noise, meaning it has a very low signal-to-noise ratio. So what we can do is use an op-amp. Here's an example of a chip, an op-amp, very popular one, UA741. Anyway, so we can use an amplifier in order to boost that signal-to-noise ratio and give us something that we can scope more easily or do something else with, whether that's save it digitally or communicate it to another subsystem. This is the common circuit symbol we use for an amplifier, and this configuration right here with the external resistors is called the integrating closed loop configuration. And so the gain for that op-amp is shown right here. The output voltage is, the amplitude of it is increased by a factor of RF over R1. So you see that, and I don't want to talk too much about this now, it is a topic we will discuss later, but you see that the ratio of the external resistors is what actually determines the gain. Okay, moving on. Diodes. Diodes allow current to flow in one direction only along a given path. An LED, light-emitting diode, is one that gives off light. So this is the symbol we generally use for a diode. It has an anode and a cathode, the positive and negative ends, and we expect that current will flow only from the anode to the cathode. What happens when you apply a reverse voltage across it, one that would push current in the other direction? It should block it within a certain range. And here are some examples of physical diodes. Generally, the shaded end, as you can see here, indicates which is the quote-unquote pointy end of the diode or the cathode. Transistors are a little bit more difficult to quickly explain. First things first, it's not really something we get into a whole bunch here in circuit analysis, but I did want to talk about it briefly. So in the most basic terms, a transistor is an electrically controlled variable resistance. Okay, we have the resistor, which is nice, but that is a static value. The transistor is a 3-terminal device with the third terminal allowing us to control the resistance between the other two. So that's what this picture here is trying to show. This is the symbol for a transistor, and the way that it works is essentially like a variable resistor where the resistance is a function of this voltage here, VG. It may also be thought of as a solid-state switch, which makes sense because if you can increase and decrease the resistance indefinitely, then you can make it into a switch. The transistor is the most important fundamental building block of modern electronics. It allows a circuit to control its own currents and reconfigure itself on the fly. Without the transistor, modern electronics would be impossible, and especially the modern computer, right? Because a resistor is nice, it allows us to control some currents, but they're static controls. We cannot change them on the fly without replacing the resistor itself. And so here's a really interesting image. This is an image of it's a transistor level design of an 8086 16-bit microprocessor, and this is the predecessor for the 286, 386, 486, Pentium, Celeron, on and on. What are the modern day, what we call the 86 based architectures, which are the same, more or less, at least the basis of what is the modern Intel and AMD i7 type, i3, i5, i7 type chips. And so you can see, even here at this early stage, so I think this was probably designed in the early mid-70s. This already contains, and again I apologize, I don't know the exact number, but thousands, if not hundreds, tens of thousands of transistors. Now, today, that number is in the millions or billions of transistors on a single chip. A capacitor is a device that stores generally small amounts of energy as an electric field. Capacitors are used to configure AC circuits, stabilize DC voltages, and design filters, kind of like a stereo EQ. We're going to talk about capacitors in more depth later on. This is the basic circuit symbol, and the VI relationship is shown right here. So the current flowing through a capacitor is equal to its capacitance times the rate of change of the voltage across it. So you can see here, if the voltage across the capacitor is static, then the current flowing through it will be zero, regardless of how large that voltage is. Over here we have some pictures of some actual capacitors, and you can see that there's several different shapes depending on the technology used and the material used to fabricate it. Inductors use a coiled conductor to store electrical energy as a magnetic field. Inductors are used for many of the same applications as capacitors. They're also used for filtering, stabilization of currents, etc. So this is the symbol we have for an inductor, and it's a similar type of a relationship, almost flipped, almost reciprocated, inversed, right, where the voltage across the inductor is equal to its inductance times the rate of change of the current through it with respect to time. And here are some pictures of some actual physical inductors. Now this is more of a symbolic, or let's say hypothetical, theoretical component. We'll talk about ideal sources. So an ideal source is one that generates a voltage that is strictly constant and unaffected by other components in the circuit. You can also have current sources as well. Although in practice, in laboratory settings or in hardware, it's much easier to create a voltage source than it is a current source. So you see fewer current sources in hardware. Probably the most recognizable type of DC voltage source is going to be the battery, and it can be characterized as below. So let's take a look at both these representations. So here we have a physical battery, right? And we can imagine that as, well, not imagine, it does have a terminal voltage, which I'm going to represent as VT. And we're going to imagine it as having a single lumped internal resistance as well as single lumped internal source. Now this is not really the way that it works. Anyone who understands chemistry and the way that a battery works knows that. But the nice thing is we can use a circuit like that to the left to represent the fundamental behavior of the battery. Again, you have your internal voltage, which we call VOC, the open circuit voltage. We have some sort of internal series resistance, as well as the terminal voltage. And so this provides us a simple and effective representation of the battery, and this is called the Thevenin equivalent circuit, which is a topic we will talk about in a later lecture. Next, let's talk about a fuse. I'm sure most of you have heard this term before, it's a protection device designed to protect from excessive current flow, which could damage more expensive transistor-based circuits. So essentially, if you think about it, it's like a bridge that collapses when you put too much weight on it. Okay, the fuse uses a conductive material that melts easily. Well, not all fuses, but I'm going to say most fuses, right? Use a conductive material that melts easily from the heat generated by higher current flows. So you can see here's a picture of an actual fuse. There's a very thin piece of conductive material in the middle, which if too much current passes through it, it'll cause it to melt. And although that will destroy the fuse, it will protect the rest of the circuit. Lastly, or not lastly, well, it is lastly, the electric motor. Now, we don't talk too much about electric motors in this class, period. That's mostly reserved for an electric motors class or a power systems course. But it converts electrical energy into mechanical energy or rotational torque / motion. There's tons of really great other YouTube resources out there, tons of really great animations that discuss how an electric motor works. And here we have a picture of a physical, actual electric motor that one would use in industry or for some commercial purpose. And so that pretty much ends this lecture. The objective here was really just to give a brief introduction to these components, many of which, especially resistors, capacitors, inductors, we are going to visit again and cover in more depth.